All right, so let's see. If the function is some constant, what's the derivative of a constant?
Like 0.
Yeah, what's the slope of a constant?
0.
I'm hearing ones and zeros. Can we take a quick poll? The slope of a constant function. My zeros, raise your hand. My ones, raise your hands. Should we draw the function?
Yeah.
All right, so what does the constant function look like? Or a constant function look like? Horizontal line? Right?
Yeah.
Okay. I'll go with that. Slope 0. All right. What about if we have something like mx plus b? What's the slope of a linear function? Does that work? People agree with that? Yeah, I probably could have convinced you that in Algebra 1. Hey, we have our first 2 rules. That's great. This is a piece of cake. It's not going to get any harder than this, is it? Let's see. This one's a little harder. Let's see how I can write it. I have to think. I think I'll write it like that. So the function is c times some other function. Now, if f of x was equal to g of x, the derivative of f of x would just equal the derivative of g of x. That's not too hard, right? If the functions are equal, then the derivatives are equal. What if the function is c times g of x? What's c do to g of x? All right, magnified, weird word, but okay, it does something to it. Oh. Stretch? Vertical stretch? Is that all right? Okay, that's true. It's a vertical stretch. Okay, so Alicia, can you say that again? Because that's a great question. It's probably what I would have just asked. The same what? The same what? What's a name? Slope? Okay, well all right, that's a great question. That's what I thought you were asking. I didn't know what it was. So the question is, do f of x and g of x have the same slope at the same spot when we stretch it vertically?
That's not what I meant.
Oh, well, it was a great question if that's what you had meant. I don't know what's its name. Zeros. Yep, yes, that's true. All right. All right, so wait, we want to take a look at maybe what this would look like. So there's a function, we can call it f of x. And do you want g of x to be like a stretch or a compression? It doesn't matter. No, they overruled you. So let's double the y values. So this is what, oh, sorry, I did this backward. That's actually what f of x would look like. G of x is the function before we stretch it. So f of x is some stretch of g of x. So I agree with Alicia. Alicia says the zeros stayed the same. They didn't change. Did the mins or maxes change? What changed and what stayed the same about the mins or maxes? X values, it's more minimum or maximum, so the y values are what's changed. And that's actually the important thing. A vertical stretch changes what? The y values. So how's that going to change the slope?
Make it smaller.
All right, it's going to increase or decrease depending on what c is, depending if we stretch or compress. Yeah, so actually, this is to say is this. The slopes are almost the same. It just steeper or less steep by a factor of c. So a constant really doesn't change anything other than multiplying the slope by the constant. Okay? Yep. Right, so if the original function had a slope of 3 at x equals 2, and now we're looking at double the function, the slope's going to be 6. Why? Because the y values are increasing at twice the rate. It's twice as steep. Okay? How are we doing? Yeah. All right. You haven't shown me anything that's interesting yet. Okay. And then finally we have the power rule, right? And that's going to be n times x n minus 1. And I could say, we could write these all in Leibniz notation. So another way of writing this would be the derivative with respect to x of x to the n equals n times x to the n minus 1. Right, so this says the same thing in Leibniz notation. Doesn't matter. In the back of your book, the very back cover, there's a list of like 10 derivative rules. We're going to learn them. The power rule's there, right? So I think it's on the paper thing. Is it there, right? Yeah. It's there. Yeah, isn't it? Isn't there a list of derivatives? Yeah, Kelly confirms. I'm not lying. All right, Sam and then David.
It's kind of off topic, but do we have to know the different formations for whatever?
I have no idea what you're. I have absolutely.
Like, do we need to know both?
Oh, notations?
Yeah,
you definitely should. Like, you can write it however you want, but if I write this, you have to answer that. You have to be like, oh, I know what that means.
Okay.
Right? So you can write it however you want, but you have to be able to read it however I write it. And I'll probably write it in both ways. David?
You know what? Never mind.
All right. So, probably bears mentioning now. This chapter will have lots of quizzes, probably 3 or 4 quizzes, and every quiz and test will be without a calculator, so you have to memorize. You have to.
The test is without a calculator?
Yep. And the test is different from this chapter's test.
Is it a one-day test?
The test is a one-day test, and it's going to be 10 problems, and you have to get 8 out of 10 of them right, or else you have to come back and take the test again. It's like a gateway test. It means you have to show proficiency with it, all right? Which actually means you're guaranteed at least an 80% on the test, okay? Now, there are a few rules with it. I'll tell you right now, but I'll tell you more when we come up to the test. The first time you take the test, you can pass with an 80, a 90, or a 100, okay? The second time you take the test, you're not eligible to get a 100 on the test. You can only get an 80 or a 90, because it wouldn't be fair if someone passed it the first time and you did better than they did. The third time you take the test, you're only eligible to get an 80, and every time thereafter. Okay, so if you're gunning for the 100 or the 90%, you got to pass like the first or second time. Otherwise, you'll pass the third, fourth, or fifth time with an 80%, and you're guaranteed that. But you got to keep taking it until you do that. All right, David and then Dan. No.
How many people have to retake this?
I find that the people that ask that question are usually the ones that have to. All right. So I want to talk a little bit about the power rule. And no, isn't that a bummer? Now, Katie, did you ask? Now, I'm lenient on the quizzes. Like, it's not all or nothing on the quizzes. So I'll like circle what you got wrong and give you partial credit on those. But when it comes down to the test, you can be off by like a minus sign instead of a plus sign, and the whole thing's wrong. Isn't that a bummer? All right. So.
Yeah.
I wonder if I can. No, this isn't working. Yes. Yes, you can. Yes, you can.
There's partial credit, right?
No.
No, it's just someone.
Well, Monday.
I just thought it would be funny.
No, I mean the test on Tuesday, the second half.
Right. So on Monday, there's no partial credit. On Tuesday, if you try to answer it and you get it wrong, you get points off Monday's test. Oh, come on. What has changed? You guys are just acting funny. I shouldn't have told you anything about this test. All right. I wish this was bigger, and it's not. Okay, so I want to talk to you about the power rule, and really what I'm going to do is I'm going to just do a few examples. I don't know how to.
Right there. Right there. No, get out of that other thing. See?
I'll try. I don't think that did anything. No.
I think it did, actually.
It did, actually.
It did. You have to go really big.
Okay, I think you're wrong, but I'll do it again. Oh man, that's huge. You're right. Okay.
I think I said you have to go really big.
All right. I don't know. So we're just going to deal. Okay. We can sort of read it. Yeah, we can suck it up. So if the function's x cubed, I just want to show you that we have the derivative. If we did it algebraically, we would be looking at f of x plus h minus f of x all over h. And let's see. Nope, that's not what I want. So if we have f of x equals x cubed, and now we do the limit as h goes to 0 of f of x plus h minus f of x all over x plus h minus x, the denominator is a piece of cake, right? I'll do that. Gesundheit. And actually, part of the numerator is not bad at all, right? The minus f of x part. It's just you probably don't want to cube x plus h, right? You could, and if we did, let's see. I'm going to see if I can do this cleverly. All right. I think I can do this. What if we make this? Nope. Oh, it won't let me make it bigger? I've never seen that. That's a bummer. All right. So, and then minus x cubed. Let's look for patterns that happens. The first thing that happens, x cubes go. The next thing that happens, what can I do? Take out an h. So that's an important pattern to remember. We can take out an h, and when we take out an h, we're left with 3x squared plus 3hx plus h squared. What's the only term that doesn't have an h in it? Okay, the first term. And as h goes to 0, we're left with 3x squared. All right, that's the pattern. Let's take a look at what happens when we change this to something like x to the 4th or x to the 5th. All right, we get more terms, right? But we can still do this. Well, see, I'm trying to show you that the power rule is true, is what I'm trying to do. So, David, you will eagerly agree with the book, but you will not agree with me. Is this what I'm hearing?
Well, the book is published.
All right, and I'll do this part. This part's easy, minus x to the 4th. I'm going to grab... I need to grab this piece. Oh, boy. That's a mess. Let's see. Oh. Oh, boy. All right, hold on. Hang in there, please. Okay. Now I can grab it. Okay, so let's look at things that happen. The first thing that happens, the x to the fourths go. And then what am I going to do? When I factor out they all have an h. What's the only one? The first term doesn't have two h's in it. So in effect, the h's go, and then everything else, when h goes to 0, goes to 0. And I'm left with 4x cubed. And in essence, I'm always going to be left with just the term that has one h in it. So we can go back to this, and we can look for patterns, right? So just all you want to do is look at the term that has an h in it, right? So if I change it to something like x to the 17th, that's a lot of algebra, but where's the term with one h in it? 17 hx to the 16th, right? Yeah, I agree. So can you see that pattern holds? I didn't prove anything to you. All I did was show you 4 or 5 examples, but do you understand that we could keep doing it, and that's what would happen? All right, so we know the rule now. We're ready to get lots of practice. So we're going to do like 15 examples of the power rule. All right, so let's see. There are lots of interesting things about this chapter. Another interesting thing, it does work. No classwork for this chapter. Some people like it, some people don't. It is. It's very different, right? No classwork. Uh-huh.
I usually take this on the after. New territory.
What's this called? Shortcut chapter?
Yeah, pretty much. All right, number 1, who's up? Morgan! What's the derivative? Perfect. Nice. Calling someone, Morgan.
Is the derivative of that 1 over root x?
Talk to me how you got it. It's almost right.
Same thing, or wait, yeah, that's the same thing as x to the 1/2.
Okay, hold on. No, you're right. Hold on, just let me catch up with you.
Sorry.
Okay, so it's the same as x to the 1/2. That's correct. Okay.
That ends up being 1/2 times x to the negative 1/2.
All right, so 1/2 x to the negative 1/2.
Which would end up being, 1/2 times 1 over x.
Okay, and I'm just going to say 1 over 2 root x. Either of those are correct answers, right? You can make your Algebra 2 teacher happy by doing 1 over 2 root x. Or actually, would your Algebra 2 teacher freak because you had a radical in the denominator?
Yeah, maybe freaking either way.
So you could do, what? Thanks, that's what I wanted to say. You could say root x over 2x. All 3 answers are fine. So look, if you're taking a quiz or a test, why don't you just quit while you're ahead? Did I tell you that joke already?
Yeah.
Okay. No, it's all right. No. You should just stop there, right? You can simplify if you want. Now, here's the trade-off. When you're checking in the back of the book, they may or may not leave it in any one of these forms, and you can't freak out that if you got this answer and they give you this answer in the back of the book, like, oh, I got it wrong, I don't know what I'm doing. Like, you have to be willing to, like, simplify if you want your answers to look like the answers in the back of the book. See, I don't think I'm going to do that. I think you're going to do that, right? I'm not going to give you the answer and say which one's the answer. I'm going to say, here's the function, tell me the derivative, right?
No, I think what she's saying is like
No, but
multiple
like
choice.
on a multiple choice test, like we have multiple choice. There's not. Oh yeah.
Like, I could definitely do that down the road, but this chapter is not going to have a multiple choice part, right? If I wanted an easy question on like the mid-year exam, yeah, I could do that. I could be like, here's the function, which one's the derivative?
And we could just like all the above and put all this.
Yeah, you'd love that. All right, thanks, David. Calling someone for number 3.
The derivative equals e plus 2x
Good. That was the first function that we did that we had lots of pieces to, and all Drew did was take the derivative of each piece. Yeah. How do you feel about that? What?
All constants just go.
Yeah, we haven't done one like that. Maybe we'll do that next. Does anyone have, before we look at number 4, does anyone have a question on number 3? Because that was, I would say 2 and 3 are both sort of variations on the power rule, but a little bit extra, right?
No, it makes sense.
Okay. All right, Drew, calling someone to take a look at 4.
Would it be e x to the e minus 1 plus e pi to the e minus 1? E pi more than
How? Well, what's pi? What's pi to the e?
some other number?
Some number. What's the derivative of some number? Try again.
0.
It's 0.
Yeah, this is a constant.
Right? Didn't you tell me the derivative of a constant was 0?
You only do it to once with x. It doesn't have a variable the h.
So e to the pi is just a number like 12, right? I mean, it's not 12, but it's just some number, and the derivative of a constant is 0. So that's tricky, right? I like it. I like it. Now you see what Dan did with the x to the e? He just brought the exponent out in front and decreased it by 1. He just used that rule.
Would it be okay to leave with e minus 1?
Yeah, like that? Definitely. Yeah, I would stop there. All right, let's see. All right. Okay. Dan, who's up for 5? I think so. That works, right?
Wait, why would it be, okay, so if it's 4, wouldn't it be 4t to the 1?
Right.
Yep.
And then 1 times 4, and then t2. Right, okay.
Is that okay?
Yeah.
So it
I
does
thought
work.
The whole thing from 0.
No, so it's just the t, just the variables to that. You decrease that exponent. 6. Alicia, who's up?
3 halves root x plus root x over 2x.
How'd you get that? That's crazy talk. You're crazy.
So the root x is x to the 1 half.
Okay.
And when you multiply x to the 1 half by x to the 1, it's x to the 3 halves. And then it's root x when you multiply through 1.
Okay, so hold on. So here's something that's interesting. You don't have a rule for the product of two functions, right? This is the product of two different functions. The only thing you have a rule for is power functions, like x to some number. This is x to some number times x plus a number. I could ask you the first piece or the second piece, but as a product, you don't have like a rule that does products. and it's actually interesting. After we get the answer that Drew gets, let's go back and see if we could have just taken the derivative of this piece times the derivative of this piece. Okay? I'm thinking it's not going to work. Just my guess. So Drew says you have to do some algebra before we even get the answer. So now Drew gets it in derivative-friendly form, right? This is ready for the power rule. All right, I'm ready, Drew.
And so you bring down the 3 halves, and then it would be x to the 1 half, which is the same as 3x. And then you...
All right, so 3 halves x to the 1 half plus...
And then bring down the 1 half, and then that'll be x to the negative 1 half.
Great. Now, you can totally change this, right? You can make this happy for your algebra teacher and do this. But you can leave it in the first form. They're both correct answers. They both say the same exact thing. And I mean, the secret lie is mathematicians don't care, right? Your Algebra 2 teacher may have cared, but mathematicians really would leave it either way, and they don't really care. I don't know. We needed to teach you, to have you do something, right? And we needed to be able to take points off on a test or something. I don't know. Pretty much. Well, all right, so here's the thing, David. You still need to know, right, if I write it like this, that it means that. And if we didn't teach you how to simplify things, you would think that these are two totally different answers. And that's not a good thing, okay? So it's important for you to be well-versed in how to express the same idea. But I think once you get to this point in your mathematical career, the freedom is you get to decide how you want to express it, okay? Questions for Drew? That was a tough one. All right, Drew, who's up for 7? No, that's backsies. You can't do backsies.
No.
Negative m to negative second.
Negative m to the negative second. How'd you get that?
Because it's m to the negative 1.
So this is really another way of saying m to the negative 1. So Sam took the exponent out in front and then decreased negative 1 by 1 to get negative 2. Great. Every year around this time, I get someone who raises their hand and says, well, can't I just have a scientific calculator on the test because I don't know how to add or subtract negative numbers? No, you may not. No. This is a good time to remember how to subtract fractions, how to add or subtract negative and positive numbers. All right. Sam, call on someone.
Rachel.
So, you can use the power rule for the first number, so it's 2n. And then the 2 to the pi is just a number, and pi to the squared is just a number, so it just becomes that.
Nice. I didn't fake you out that time. I'm a little upset, but that's all right. Good. 4 more. You want to ask a question before we go on? So you like this? What does that mean? Yeah.
I thought that. I thought.
You sure?
Yeah.
Okay. Yeah, so I think there are some people that actually enjoy this. And you probably know who you are.
I do too, but I like
Of course.
That's supposed to be an R, sorry. All right. Who just went? Who's up?
No.
Number 9, would that be 2x times x, or negative x?
2x times.
Negative x.
It wouldn't be. And actually, we should have gone back here and asked ourselves, for 6, the derivative of root x is 1/2 times x to the negative 1/2. What's the derivative of x plus 1? 1. 1. You can't just take these two and multiply them together. If you did, this is the only answer you'd get. There's something, since we have a product, it's a problem. And I'm going to say the same thing to you, David. We have a quotient, and that's a problem.
Right.
So you have to split up.
That's what I did.
Is it? Oh, talk to me. Then maybe I just wrote it down wrong. Go ahead. Hold on. Tell me what you did, David.
I split it up into x squared plus 1 times over x.
Oh, okay. So all right, that's not a bad start, though. It's just that if you want to split it up like that, you can't do the product. So you got to do something first. So talk to me, David. What can we do?
Well, 1 over x is x.
Okay. You got a couple, I think 2 or 3 people that'll give you, point you in the right direction.
If you distribute out the x to the negative 1,
Okay.
you would get x plus x to the negative 1.
Okay, so we have to distribute x to the negative 1 times x squared. What do you get when you multiply? What do you do with the exponents? Add them, right? Now, you could have also just split this fraction up. You could have said that this is the same as x squared over x plus 1 over x, which is x plus x to the negative 1. There are lots of algebraic ways to get to the point where the function's ready for the power rule. And now we're ready for the power rule. All right, David, how about we go back to you for the power rule now?
That would be 1 plus negative, or 1, yeah, minus 1 over x squared.
Okay. So 1 minus x to the negative 2, or 1 minus 1 over x squared. Say the same thing. Okay, this is the same as 1 minus x to the negative 2. Tricky, right? How do you get where? Exponent out in front, negative 1. Decrease the exponent by 1, negative 2, right? How would your Algebra 2 teacher write it? Like that. All right. All right. So you need to